Okay, so maybe it'll be good to recall what we've done and what we're planning to do. So if you remember, we were discussing averaging operators in dynamical systems and effective ergodic theorems. We then talked about unitary representations, operator norm estimates, and counting lattice points. And in the third talk, we also gave basically a full proof of the counting lattice point problem and an indication of the proof of the effective ergodic theorems. And we then talked about the notion of the effective ergodic theorem for Lie groups and the spectral transfer principle. We never got around to the duality principle, but we're going to talk about it today. And in general, we're going to talk about fast equidistribution of dense lattice orbits and best possible Diophantine approximation on homogeneous algebraic varieties. And it's not going to be a big surprise for you that we have a secret weapon on how to approach best possible Diophantine approximation exponents, which we're going to define. And okay, so this is of course going to be connected to our spectral estimates. So let me briefly continue where we stopped last time, that it's a remarkable feature of unitary representation theory of simple groups that the best possible spectral estimate can be realized very often. And this was observed already by Kazhdan, as we noted, and in fact served as the cornerstone of his proof of property T. Kazhdan considered the subgroup L, which is the semi-direct product of SL2 and R2, and the restriction of a general unitary representation pi of G without invariant unit vectors to L. And then pi restricted to L has no pi R2 invariant vectors, since matrix coefficients of pi decay to 0 at infinity. And then by Mackey's theory of unitary representations of semi-direct products, the restriction of pi to L is induced from a unitary representation of an amenable subgroup of L. This key observation is in Kazhdan's original argument. And it follows from that that pi restricted to L is weakly contained in the regular representation of L. And as we saw, and the conclusion of that is the restriction of any unitary representation of G equals SL3R without invariant unit vectors to SL2 is a tempered representation of SL2. And we have seen that this means that in every ergodic action of G equals SL3R on a space X, the averages beta T supported on BT contained in SL2 satisfy the best possible spectral estimate. For example, if gamma is a lattice subgroup of SL3R, the ergodic action of SL2, this is not a transitive action, this is a properly ergodic action. SL2 acts on SL3R modulo gamma, but this action has the truly remarkable property that it has the fastest possible rate of convergence to the space average. And it's therefore natural to define the following for general G and non-amenable H. We call the triple GH pi tempered if the restriction of pi to H is a tempered representation of H.
What is tempered?
Weakly contained in the regular. And H is a tempered subgroup if it has the even more remarkable property that every unitary representation of G without invariant unit vector has a tempered restriction to H. This is truly a remarkable phenomenon. And, for example, Kazhdan has proved that SL2 is a tempered subgroup of SL3. Okay, so there are several robust and easily verifiable general principles which can be used to establish subgroup temperedness. And we will briefly recall, very briefly recall some of them, so that you'll see this is not some very rare event. So Kazhdan's original semi-direct product argument can be generalized. One formulation is that when SL2R, semi-direct product with RD, is a subgroup of G, then any unitary representation of G without RD invariant vectors is tempered when restricted to SL2. For example, this can be generalized to other fields, to p-adic fields, and various other situations. Now, when G is simple with property T, there are universal pointwise bounds on the k-finite matrix coefficients of G in general unitary representations. This goes back, well, I guess I should have written also to Harishchandra. Certainly, some estimates like that appear in Harishchandra's work, at least for certain unitary representations. It was studied systematically by Cowling and Howe Moore and Howe Tan, Jean Chouli, Heo, and other people. And for example, in Michael Cowling's talk, we basically saw some version of these universal pointwise estimates where the matrix coefficients of a unitary representations are estimated by a certain sum with leading exponents. So this is a very successful theory, and there are very useful and universal bounds. Now, these bounds apply to all, say, k-finite matrix coefficients of G. And it may happen to be the case that when you restrict these bounds to a subgroup H, you have a function on G, the universal pointwise bound. You restrict this function to H, and it turns out that it's L2 plus epsilon in H, or on H. There's no reason why this shouldn't happen, although there's no reason why it should. And so if, in fact, the restriction to a simple subgroup, let's say H, is in L2 plus epsilon H, then every restricted representation of H is tempered. And Margulis in 1995 observed that this holds for the images of all the irreducible linear representations of SL2 in SLN. So what I mean by that is the following. Supposing that you take the group SL2R, it has a unique, irreducible, linear, finite dimensional representation, one in every dimension. You throw away the representation in dimension 2 because there's no bigger group there, and you start with dimension 3, the representation of SL2 in SL3. Now, this is completely different than what Kazhdan did, because the copy of SL2 that Kazhdan considered is reducible. It has an invariant subspace. I'm talking now about the opposite situation. I'm talking about an irreducible representation of SL2 in SL3. That's going to give you a certain copy of SL2 in SL3. And Margulis observed that the restriction of these universal pointwise bounds, or a general unitary representation of SL3, is a tempered representation of this SL2. So you can see here a very interesting phenomenon where you are successful if SL2 is reducible, and you are successful if SL2 is irreducible. Of course, SL2 is a little bit special, but this observation can be greatly generalized. You can consider, for example, the representation of SL3 in SLN. And these representations are also typically, I mean, the image of a finite dimensional representation of SL3 in SLN is also typically a tempered subgroup. Now, as we've already seen a number of times, unitary representations of simple groups have matrix coefficients in L2kg for some k. We've discussed this at length. We had all these tensor power arguments. And so restricting a representation of g to the k to the diagonally embedded copy of g will give you matrix coefficients which are products of the matrix coefficients, and so they will be in L2 plus eta, let's say, or L2, whatever. So the diagonally embedded subgroup is also tempered in this big group. I mean, well, okay, here I have to be a little bit careful. I mean, really, well, yeah, what I've wrote here is not strictly true, because it's not a subgroup which is tempered. It's tempered with respect to irreducible representations which are irreducible on the factors. In other words, you can take a representation of gk which is trivial on one of the factors. Okay, so I'm just mentioning this, but in principle, if you want a good example of this situations, you can take an irreducible lattice in g to the power k and look at L2 g mod gamma. This is a representation of g to the k which is good. Its restriction to the diagonal copy is tempered. And for some lattices and their low-level congruent subgroups, the Selberg eigenvalue conjecture is known to hold, so that L2 naught of g mod gamma is known to be a tempered representation of g. And this holds, for example, for SL2z in SL2R, or for SL2zi in SL2C. This is however, this is a limited source, because the Selberg eigenvalue conjecture is extremely difficult and it's open. It gives there's some instances where it holds, but this is a very important source of examples, because these gives rise to very interesting results. But in general, the Selberg eigenvalue conjecture is open. Okay, so now we're going to pass to an application of all these spectral estimates. I put a lot of emphasis on the idea that if you have representations of G, they can be tempered when restricted to H. Now, why are we interested in this property? In order to explain this, let's talk a few minutes about one of the most fundamental problems in ergodic theory. And this is the problem of approximation on of approximation by dense group orbits. Okay, so the general setup is as follows. Let G be a locally compact second countable group, gamma a discrete lattice subgroup, and let H be a closed subgroup. And we assume that gamma is ergodic on the homogeneous space G mod H with respect to the unique quasi-invariant measure class. Maybe I should anticipate the future and say that this is equivalent to H being ergodic on G mod gamma. So once again, the ergodicity of gamma on G mod H is equivalent to the ergodicity of H on G mod gamma. This is perhaps the most primitive example of the duality principle. And you all realize that in that case, the fact that gamma is ergodic on G mod H is a non-condition in our case, because if you remember, for the case of simple groups, we have vanishing of matrix coefficients, and so every non-compact subgroup H of G is ergodic on G mod gamma. So this condition is extremely, extremely mild. Now, in that case, it's an exercise in classical ergodic theory that if the gamma action is ergodic, then almost every gamma orbit in G mod H is dense. And now, let norm G denote a natural gauge on G, namely a continuous non-negative and proper function from G to R plus. And let D denote some natural metric on G mod H. And we would like to analyze the efficiency of approximation by gamma orbits on the homogeneous space G mod H as follows. Let's fix a point x in G mod H and suppose that for sufficiently small epsilon and for every x naught in G mod H, we can solve the inequality that the distance of between gamma inverse x and x naught is less than epsilon. In other words, we have a gamma orbit. We have a gamma orbit, the gamma orbit of x, and the gamma orbit of x is typically dense. And so supposing that we have established that we find some gamma that takes x close to x naught, up to epsilon. Now, we want to analyze how efficiently can we do this. And the way we measure this, we would like gamma to satisfy that the norm on gamma, I use the word norm to denote that gauge. This will be usually a norm in practice in our examples. So we would like the size of gamma, the norm of gamma, to be bounded by 1 over epsilon to some power zeta, where zeta is a function of both x, x naught, and of course g, h, and gamma, and is finite. So we would like approximation to a general point by dense orbits with polynomial efficiency. So this is a this is a very stringent condition. In general, there is no reason to expect that this zeta is in fact finite. And this is certainly not obvious in any of the examples, or in most of the examples we'll discuss. So we certainly want it to be finite, and even if it we want to have this polynomially efficient approximation. Now, supposing that we were able to actually realize this, then so zeta x x naught is the rate of approximation of a general point x naught by the gamma orbit of x. And so this brings us to the following problems. The first problem is finiteness. We would like to have a finite constant zeta, which depends only on gamma and the variety G mod, the homogeneous space G mod H, which bounds the rate of approximation by almost every lattice orbit. And we can even more ambitiously ask whether we will have such a finite uniform bound for every single lattice orbit without exception. I can tell you already that this is not going to happen generally. There are obstructions to that, but perhaps there would be some situations where it can be realized. So this is a much stronger conclusion where our approximation actually holds for every single gamma orbit, and not just for almost every. Another problem is to compute explicit bounds, namely to establish an upper bound and a lower bound on the rate of approximation and explicate their dependence on G, H, and gamma explicitly. And problem 3 is the problem of optimality. We would like a simple and easily verifiable and widely applicable criterion for when the upper and lower bounds coincide. And then we will have the optimal rate of approximation by lattice orbits on the homogeneous space. Now, the scope of this problem is very large But I have, I mean, in this series of talks, we try to keep things quite general because actually, as you will see, there are some very general principles at work here. And I wanted to emphasize them. They don't depend so much on the various arithmetic details. But since I haven't given examples in this course almost at all, and I feel really very, very guilty about this, let us say a few things about the scope of this problem. So one possibility is to take G to be the real points of a real algebraic group defined over the rational field, and HR to be an algebraic subgroup, and gamma to be the lattice of integral points. And this, when we do this, our problem includes natural Diophantine approximation problems on homogeneous affine varieties, as well as on homogeneous projective varieties, because so far I haven't said anything about what the group H might be. It's legitimate to ask for the question of approximation of points on G mod H by elements of gamma, whatever H is. So, for example, G mod H may be a projective variety. Now, we all realize that every group G, well, okay, the simple groups G, for example, that we were discussing has an enormous variety of subgroups. If you think about SL3R, you can have, for example, approximation on projective space. Well, you can start by the affine action, you can, or the linear action on Rn, the affine action on Rn, etc. And it has various subgroups. Some of them are solvable, some of them are nilpotent, some of them are simple. For example, SL2R is a simple subgroup of SL3. And all of those give you homogeneous algebraic varieties. Okay, now another possibility is to take G to be a connected Lie group, and H to be a closed subgroup, and gamma to be an ergodic but not necessarily arithmetic lattice. And this includes, for example, H being a lattice subgroup itself. And for example, it includes also lattice orbit approximation on locally symmetric spaces when G is semi-simple, say. So here we made a big change. In the first part, H was an algebraic subgroup, but in the second part, H is a closed subgroup. So it may even be discrete or a lattice, but this still gives a homogeneous space, and the question of approximation by lattice orbits is a very important problem in homogeneous dynamics. And another possibility is to take G to be a so-called S-algebraic rational group defined over the rationals, and H a closed subgroup, and G to be the lattice which is defined by the S integers. So, for example, this includes groups like GR times GQP, and we can then take H to be GQP. So then we are trying to approximate, for example, on the group variety, referring to what you said yesterday, we're trying to approximate on the connected group variety GR by the dense subgroup GZ1 over P. And one can consider more general homogeneous spaces. And finally, we can consider GA and edge A to be groups of rational adels, and gamma to be the group of rational points. And this problem is a very interesting problem. It includes the problem of intrinsic Diophantine approximation, namely by rational points lying on the algebraic variety GR modulo HR itself. This is, in this particular case, our lattice gamma happens to be the group of all rational, let's say, matrices. So approximation by gamma orbits would amount to approximation by rational numbers, which is the most classical aspect of Diophantine approximation. You want to approximate real numbers by rational numbers. The point here is that you want to do it on some homogeneous algebraic variety, like a sphere or a hyperboloid or a vector space, using points on the variety itself. And of course, other natural examples would involve groups over arbitrary locally compact fields, p-adic fields, and lattices over arbitrary number fields and not necessarily rationals. And other natural problems will include establishing an analog of Khinchin's theorem when the rate is optimal and other further refinements. And what we're going to do now is we turn to describe a general approach to the problem of establishing explicit bounds, and we're going to give a sufficient condition for optimality under certain conditions. And of course, a main assumption in our approach is that G is non-amenable. There is nothing that I'm going to say here that is not in principle valid for, let's say, abelian groups. But the results are very weak. Abelian groups, one can approach them with a lot of other methods. And I certainly wouldn't advocate this method in that case. This method is interesting, really, primarily when G is non-amenable. Although, maybe for complicated solvable groups, for example, these problems have not been discussed before, so one can get some results from this approach. But definitely the main interest is when G is non-amenable. So some previous results on approximation exponents. So Loren and Noguera in 2011 okay. So yeah, I have some issue here with the zeta and the kappa. Sorry? Kappa, I hope, kappa will be defined in a moment. I thought it was already defined. In any case, Loren and Noguera established this polynomial bound. And the zeta, okay, the zeta, they have bounded by 3 for a very simple, and really one has to say a classical case. You simply look at the group SL2Z acting by linear transformations on the plane. And in that case, you have, in that case, almost every orbit is dense. And one can ask the question that we had before. The plane is a homogeneous, the plane minus a point, is a homogeneous variety under SL2. It can be identified with SL2 modulo the unipotent group. Gamma, which is SL2Z, acts on this homogeneous variety. And you can ask, how big are the matrices in SL2Z that you need to take in order to approximate by your dense lattice orbit? It's a really very concrete, very classical issue. And so Loren and Noguera gave a bound of 3 for the power of 1 over epsilon. Mokorant and Barak Weiss gave an explicit but not as sharp upper bound for zeta or kappa for arbitrary lattices in SL2. Loren and Noguera considered only SL2Z, and their approach was via continued fractions. Mokorant and Weiss considered an arbitrary lattice. This is a considerable generality, a considerably more general, but the exponent is not as sharp. And for S-arithmetic lattices, GZ with the reciprocals of the primes in S added, including GQ acting on homogeneous varieties of the form G mod H, where G is semi-simple, the exponent was estimated and in some cases shown to be optimal and satisfy an analog of Khinchin's theorem in previous joint work with Gaussian and Gorodnik. So we observed that one can apply spectral analysis and the arguments I'm going to present to Diophantine approximation. And we considered the case of, mostly the case of all rationals, or perhaps a subset of the rationals which is described by a certain subgroup S. And subsequently, Kleinbock and Merrill have established the best possible exponent for rational approximation on the unit sphere in any dimension n greater or equal than 2. We were only able to establish the best possible estimate in this case for dimensions 2 and 3. And they also proved an analog of Khinchin's theorem in Diophantine approximation and even sharper results. And more recently, Fishman, Kleinbock, Merrill, and Simmons considered general quadratic varieties. But other than the results that have been presented here, I'm not aware of any other results on this problem. This is actually quite surprising because the problem of Diophantine approximation on homogeneous algebraic varieties has been raised already in 1965 by Serge Lang. And it has been studied with really a lot of, I would say, persistence in many different situations where one considers various abelian groups, but it has not been studied in the non-amenable setup. Okay, so I want to be very concrete about the Diophantine approximation problems that we're going to consider, partly because we had so few examples before. So let G be an algebraic Q subgroup of SLN F. So F here is the reals or the complex or the p-adic fields. And gamma a lattice subgroup, for example, the lattice of integral points, GZ inside GR. We fix a norm on Rn and Cn and on matrix space. And in the local field case, we take the standard valuation on the field and the standard maximum norm on the linear space and on the space of matrices. This is all very standard. And we consider an affine subvariety V in Fn, which is invariant and homogeneous under the G action. So V is a homogeneous space. V is of the form G mod H, where H is the stability group of some point. So it's an invariant and homogeneous variety. And we assume that almost every gamma orbit is dense in V. And then we restrict the norm chosen on Fn to V. Now, if this sounds abstract, all you need to do is think about SL2Z acting on the plane. So this is definitely an example which is complicated enough. And so, okay. The linear space minus a point is also an example. And then we consider the Diophantine inequality, which is the norm of gamma inverse x minus x naught is less than epsilon, with gamma in gamma satisfying the norm bound, norm gamma less than b to the b times epsilon to the minus zeta. And we define the Diophantine approximation exponent kappa as the infimum of zeta, such that the foregoing inequality has a solution with the property stated. So kappa is the best possible zeta, by definition. And kappa is what you would like to estimate. Now, the first observation is that kappa xx naught is a gamma times gamma invariant function. And so it's almost surely constant when the action is ergodic. And kappa depends, of course, on G, gamma, and V, but not on the norms chosen on Fn and MNF. So if you were wondering whether the Diophantine approximation problem is very sensitive, so some points can be estimated by a certain power of 1 over epsilon, but others will not be able to be approximated by this power, it may well be the case. It may be a very complicated picture in terms of Hausdorff dimensions, etc. But there will be an almost sure exponent. So this is definitely the first step to try to understand what that might be. So, for example, we can now consider the affine action of gamma, which is SL2Z times Z squared on R2. Not the linear action, but the affine action. And here, the optimal rate is kappa equals 1. So in fact, more precisely, for every vector u naught comma v naught in the plane, and for almost every vector x equals uv in the plane, and for every epsilon sufficiently small, it is possible to solve the Diophantine inequality gamma inverse x. Here it is. Gamma inverse x minus x naught less than epsilon with the norm of gamma bounded by b over epsilon. So 1 over epsilon. And there is a certain, this is written incorrectly, I'm sorry. The 2 plus eta should be on the log, not on the 1 over epsilon. So log squared. Okay. Okay, so, and so the point is that this is finite, which again, I mean, maybe maybe there's something I'm not aware of, but I don't know how one would simply prove this fact from completely general considerations that the exponent is finite here. So what we're saying is that the exponent, the optimal exponent is in fact, it's finite and it's 1. That's the optimal exponent. And now taking the two resulting inhomogeneous equations mod 1, we can conclude that for every u naught comma v naught in the 2 torus, and for almost every other point x, or any other point in the 2 torus, and again for every epsilon sufficiently small, there are integers a, b, c, d, such that we have this simultaneous, two simultaneous Diophantine approximation statements in each coordinate, solved with integers a, b, c, d, such that ad minus bc is 1, namely it's a matrix in SL2Z, and the maximum, say, of a, b, c, and d is again the same bound, b over epsilon times log squared. Okay, so this is a very concrete example. Yes, let me just say very briefly, just because I mentioned the scope of this problem, that one can consider the affine action of SL2Zi over Zi squared on C squared, changing the group and the field and the lattice. And once again, the optimal rate of approximation of the gamma action on C2 is kappa equals 1. And a similar conclusion holds for the rate of approximation by SL2Zi points on C squared modulo Zi squared. And for example, the same conclusion holds for approximation in C squared by orbits of SL2O3 times O3 squared, where O3 is the ring of Eisenstein integers contained in Q square root of minus 3. However, for the corresponding approximation result using algebraic integers in other imaginary quadratic number fields, it is possible to give an upper estimate for kappa, but its exact value remains an open problem. This is a very sensitive problem. There is a very sensitive parameter associated to it, which has to do with the Selberg eigenvalue conjecture, which, as I said, is not known in every case, but as far as we are aware, this is an open problem. There's another example here, but let me skip to our discussion. So let's start with trying to establish a lower bound for the Diophantine exponent kappa. And clearly, a basic ingredient in solving the Diophantine inequalities which approximate a point x naught in V is to first estimate how many orbit points gamma inverse x are available in a compact neighborhood omega of x naught in the homogeneous variety V equals G mod H. We want to take this collection of points gamma inverse x, and in fact we want to filter them by the size of gamma, and we want to approximate a lot of other points. And the first thing you would like to say is how many orbit points are there in a given neighborhood. And so we define the empirical growth parameter of such points. We take all gamma in gamma such that the norm of gamma is less than t, and gamma inverse x is in fact in omega. And we take the log of this number and divide by log t. We take the Lim sup and the sup over omega compact, and that's the empirical growth rate. There are some orbit points. They have a certain size. Take the log, divide by log t, and we have a number, whatever it is. And now the rate of growth of such orbit points obeys the bound satisfied by the volume growth of norm balls in the stability group H, namely this A, the A that you have here, is precisely the exponent which is associated with the rate of volume growth of HT. Okay, so I should say that this is so in all the examples that in which we are successful. I'm not claiming this as a completely general fact, but now the reason for this is none other than the solution to the lattice point counting problem, because you see. The situation we have here is that we have a group G, right? For example, you can consider the plane, right? So we have a group G, and we have a certain subgroup H, which you might as well take to be, a line. And when you consider, for example, a neighborhood of the identity in G mod H, then effectively you are looking at a neighborhood of this subset. Okay? If you lift it to G, what you will get is a neighborhood of your line, of your closed subgroup. And so what we're basically asking is for the number of lattice points in such a set. But if you have a very general solution of the lattice point counting problem in G, then you will be able to assert that the number of lattice points in such a set is essentially its volume. And the volume of this set definitely grows like the volume growth in H, because you're just taking a compact neighborhood of H. So if you have a general solution of the lattice point counting problem, you'll be able to say that the number of points in the orbit, and that simply means if you lift it to G, the number of lattice points here in this strip, is essentially given by the volume growth in H. Okay. So now we conclude that the number of points available for the approximation obeys that gamma in gamma such that norm gamma less than t and gamma inverse x in omega is bounded by t to the a plus eta, whatever. And now let t denote a bound for the local growth parameter of the invariant measure on the affine homogeneous variety. Now, okay, this is needlessly complicated. Basically, I'm looking at small balls in the variety and I ask how the volume decay. If the variety is a real manifold, the volume decays like epsilon to the dimension. We've taken a more general approach, so we have to say a little bit more about local volumes, but in principle, the volume close to V naught of a small neighborhood is going to be bounded below by epsilon to some d. In the case of manifold, d is the dimension of the manifolds. But in all of our cases, we will be in a position where we will have such an estimate. Okay, so now for f equals r, the d is simply the dimension of V, and in general, in a compact neighborhood omega of x naught, there will exist an epsilon separated net of size roughly e to the minus d, epsilon to the minus d. Okay, so this is the most basic volume packing argument. If this is the local behavior of the volume for small epsilon, then in a compact neighborhood you will have roughly epsilon to the minus d elements in an epsilon separated set. Epsilon separated means that any 2 points are epsilon separated. So you can draw a ball around them, let's say, and this ball has this volume. Okay, so you can't pack too many of those inside. So this means that there are at most t to the a pigeons, and the pigeons are points of the form gamma inverse x in omega with the norm less than t. These are the pigeons. These are the points we have in order to approximate other points. And there are roughly epsilon to the minus d pigeonholes, because what we would like to do is to take the pigeons and put each one, well, to put them close to these points, these separated points. So at most t to the a pigeons and at least epsilon to the minus d pigeonholes. So if the Diophantine approximation in omega was successful and we were able to do it, then clearly t to the a is greater than epsilon to the minus d. We have to have more pigeons than pigeonholes, because otherwise there will be points that will not be approximated. So therefore we conclude that t is at least epsilon to the minus d over a. And that means that what we have is the following. Kappa, the approximation exponent, must be at least d over a. Namely, it is impossible to approximate points on V, on the variety as above, by points in lattice orbits, namely by using matrices of a smaller norm. T is what accounts for the norm. So, as you can see, this is a very soft and very simple and also very, very general argument for what should be the pigeonhole bound. You cannot do any better than this. And you can see that this is a very general argument. It really only needs the local behavior of the volume, a bound on the number of lattice points. Okay. And so, but at least now we have a target. We know, well, okay, once you prove a thing like that, you also have a conjecture. And if you're very bold, you can say that the conjecture is that the rate is always what is given by the pigeonhole bound. That's a very bold conjecture. Okay, but what we would like to do now is to derive an upper bound. And for an upper bound on the Diophantine exponent, we will use spectral estimates in the automorphic representation of L2 G mod gamma, leading to an effective mean ergodic theorem for H. Okay, so we've been discussing this the whole week. We are going to have at our disposal L2 G mod gamma. It's a nice representation of G. I can restrict it to a subgroup H, and I'm going to have a certain estimate for the operators on H. Okay. And we are going to use some dynamical arguments which are usually called a shrinking target argument, exploiting the speed of distribution of H orbits in G mod gamma. I hope to be able to say a few more things about that. But finally, and now we come to the main point, we are going to have to establish a duality, an effective duality argument. And the duality argument is going to say that if you have a really good estimate for the distribution of H orbits in G mod gamma, you can dualize this and you're going to get a very good estimate for the distribution of gamma orbits in G mod H. And that is an instance of the so-called duality principle in homogeneous dynamics, which I should say a lot more about, but I really want to formulate the theorem, so we'll see how much time we're going to have to discuss all this. So let's try to derive an upper bound. Well, at least to state the upper bound first. So consider the intersection of norm balls with a stability group H, namely HT, well, okay, these are the former BT that we had before. H in H such that the norm is less than T. And consider the invariant probability measure on Y equals G mod gamma and the averaging operators pi Y beta T, which are given as usual by integration. This time I wrote H on the right hand, the action on the right hand side with your permission. This is unavoidable. I mean, here we genuinely work on the one side with gamma and on the other side with H, and you really cannot switch. So if I want to write G mod H as I did, I have to look at G mod gamma on the left. But these are the same old averaging operators that we had before. Okay. And assume that the effective mean ergodic theorem for the averaging operators pi y naught beta t holds, namely that there exists theta positive such that, as usual, that's what we've been working for, pi y beta t acting on f minus the integral of f on y decays like a certain power minus theta of the volume. Okay, in the usual way that we've been discussing all week. And then let me state the following. So let G be an algebraic group defined over F and H a Zariski closed unimodular subgroup. Gamma a discrete lattice, and we restrict a norm on M and F to G. That's how we measure the growth in G and H. We consider the sets HT intersect H, and we assume that they satisfy the volume growth bounds with rate A. And from everything we said about the solution of the lattice point counting problem, this is not a very stringent condition, and we know how to establish it. Okay, and finally, let D denote that bound that we had before for the local growth parameter of the invariant measure. So we have exactly the same parameters. We have the volume growth in H, T to the A, and we have the local growth, local decay parameter growth, I don't know, of measures on the homogeneous variety. And we have one further bit of information, which is the rate of decay in the mean ergodic theorem that we had before. And then, yes, we assume that the averages beta t supported on HT satisfy the effective mean ergodic theorem with rate theta. So under the assumption stated above, the Diophantine exponent satisfies the upper bound, that kappa is bounded by 1 over 2 theta times the same d over a that we had before. So it's a multiple of this d over a, and the multiple is 1 over 2 theta. And the conclusion for this is that if 2 theta happens to be 1, then the lower and the upper bounds for the Diophantine exponent coincide. Now, 2 theta equals 1 is equivalent to theta equals 1/2. Okay. And and that 1/2 was a feature of our argument Because in the ergodic theorem, that 1/2 means that the rate in the ergodic theorem is like 1 over the square root of the volume. This is the magic threshold. And now we have the following corollary. So if the rate of convergence in the mean ergodic theorem for the averaging operators beta t acting on L2 naught G mod gamma is as fast as the inverse of the square root of the volume, then the rate of the Diophantine approximation of gamma orbits on the variety is best possible, and the Diophantine exponent is simply given by k equals d over a, the a priori pigeonhole bound. So, corollary 2 is that if the stability group age is semi-simple and non-compact, and the restriction of the automorphic representation pi naught G mod gamma to age is a tempered representation of age, then the Diophantine exponent of the irreducible lattice gamma of G in its action on G mod age is best possible and is given by the pigeonhole bound. So that means that we have the following, let me put another conclusion, let me reformulate in another conclusion. Suppose that you have a simple group G, for example, SL3. And supposing that you have a simple subgroup for age, for example, SL2. Then you have a homogeneous variety, and the homogeneous variety is SL3 modulo SL2. And you can take any lattice in SL3, SL3Z or a uniform lattice or any lattice that you care to take. And you can ask for its Diophantine exponent on your homogeneous variety. And this result tells you that you can calculate this exponent precisely if you know D and you know A, and these are very simple parameters. Well, D is completely trivial. A, you have to use the lattice point counting problem, but okay, that's already done. And finally, you get the right pigeonhole exponent if you know that SL2 is tempered in SL3, because then the rate of decay of the operator norm is going to be optimal. And that is precisely what you get, in this case, already from Kazhdan's original argument. Another example, because we discussed it, if you consider the irreducible representation of SL2 in SL3, that's a completely different group than we had before, but it's a certain algebraic subgroup of SL3. You have a homogeneous variety. It's a completely different homogeneous variety than the one we had before, although I guess colloquially you would still say SL3 modulo SL2, but it's really a completely different variety. And once again, you can take any lattice and you can ask for the rate of Diophantine approximation, and the result is, because of this observation of Margulis, that you get what corresponds to D over A, because Margulis noticed that the image of this irreducible representation in SLR is a tempered subgroup. And this accounts for a very, I mean, okay, these are just a few examples, but from what I've said before, there are many tempered examples, and I would like to emphasize that understanding the exact extent of the class of tempered triples is a very intriguing problem. And I think it's really very fundamental. It's a very complicated scenario because you have completely different processes that lead you to the same conclusion. On the other hand, it seems to me to be such a profound, simply stated condition, age tempered in G, that hopefully there is some conceptual or heuristic or more convincing, well, not convincing, but more understandable approach without saying, okay, maybe use one of these 5 or 6 methods.
Or illuminate.
Illuminate, exactly. Yes. Okay, so Gabriela, I think I have basically exhausted my time. Yes, more or less. More or less means 100% or maybe 105% or 2 more minutes. Okay, I'm going to use these 2 more minutes, but I'm not going to keep you... okay, so theorem G, which we had, is an instance of a general method of duality in homogeneous dynamics. And this method of duality aims to establish properties of gamma orbits in G mod H using properties of the H orbits in G mod gamma. And when aiming to establish a rate of approximation for gamma orbits in G mod H when ordered by a norm, the dual property which is most pertinent is the existence of a rate in the mean ergodic theorem for, let's say, ball averages on H acting on G mod gamma. And we've been working on this long and hard, and a general quantitative duality principles has been developed in joint work with Alex Gorodnik, which took 4 or 5 years. And actually, it yields conclusions which are considerably more precise than just the existence of a rate of approximation for gamma orbits. And in fact, you can consider a quantitative mean and pointwise ergodic theorem for the discrete averages supported on orbit points when ordered by a norm. In other words, you can look at your orbit in G mod H and not just ask how fast does gamma take you to a given point. You can consider a neighborhood of a given point, and you would like to consider all the return times, and you want to ask whether the return times are equidistributed or satisfy a mean ergodic theorem or a pointwise ergodic theorem. And that is indeed the case. However, when you actually want to prove ergodic theorems, and you can do that, what you're going to sacrifice is the optimality of the rate. An ergodic theorem requires a number of analytic compromises associated with interpolation and various other arguments. So we were really very, very happy when we realized that if you forget about the ergodic theorems and you ask a question which is really far more basic, namely, just approximate one point, don't worry about equidistribution, in that case, you do not, the analytic argument is actually a lot easier, and you don't have these obstacles, and you can actually make full use of that theta which arises in the mean ergodic theorem for G. And that's why it turned out to be an actual optimal result. We do not claim any optimality for these ergodic theorems, and I'm sure they're not, because there we had to compromise. And now 1 last minute. Okay, so the gist of the matter that is under discussion is that given x naught in G mod H, you want to place it in an epsilon neighborhood in G mod H, which has volume which decays like epsilon to the dim G mod H. And so you can now take a continuous section from G mod H to G of the natural, actually the natural fibration and not the natural vibration. And then you lift this little neighborhood to G with the same volume. And this V epsilon is covered by a small neighborhood O epsilon. And you can consider the normalized characteristic function of O epsilon, and you can periodize that little bump function just as we did in the lattice point counting problem. So we lifted a small neighborhood, and we now periodize phi epsilon, and now phi epsilon becomes a function in L to G mod gamma. And if it's a function L2 G mod gamma, you can certainly operate on it by the averaging operators. And you have an effective mean ergodic theorem. And so the effective mean ergodic theorem basically tells you that this family of functions converge at a definite rate to a constant function. This constant, the integral of phi epsilon. And since phi epsilon is a periodization, one can conclude an equation very similar to what we had before. And really all you want to establish is that for some gamma here, you will have a non-zero value, because that would mean that for some gamma whose norm is less than t, you have a point close to this original point. So gamma u is going to be close. If chi epsilon gamma u h is non-zero, then you have a certain point gamma in ht which mapped u close to where you wanted to go. So thank you very much for your attention all this week, and thank very much to the organizers again for this opportunity.